Sure.
All right, so it's my great pleasure to introduce Professor Salamanca-Riba. Did I get that right?
Yes,
Okay, good. Who is an expert in characterizing semiconductor nanostructures, particularly, I believe, for nanocrystalline materials of one form or another. And so she was kind enough to come up from University of Maryland today to tell us a little bit about how that all works. So, please.
Thank you. Can you guys hear me okay? Yeah? Okay, good. So first of all, thank you very much for the invitation to give a talk here at the summer school. This is nice to see so many people here. So I'm going to talk about transmission electron microscopy and electron energy loss spectroscopy for the characterization of wide bandgap semiconductor heterostructures. And again, I'm at the University of Maryland in College Park. So the outline of my talk today, I will say briefly something about the motivation of why to do research on wide bandgap semiconductors. But I know that you already heard quite a bit of that on Monday from Jim Speck and Michael Spencer. So I'm not going to spend that much time on that. But I will say something about the materials that we actually look at at the University of Maryland. And then I will talk about, make sure it's working, our transmission electron microscopy results in particularly on silicon carbide with silicon dioxide for MOSFET devices. And we're basically in the interfaces between the oxide and the silicon carbide and how they behave upon annealing, especially on their nitric oxide annealing, or also on their phosphorus and boron annealing, and how that improves especially the charge carrier mobility. And we see the effect on the interfaces. So we'll do hyperspectral imaging, which is a form of machine learning for signal deconvolution and to characterize the structures and to see what are how the compositions of the materials is changing around the interface. And we also investigated different substrate orientations for the growth of the silicon dioxide. Then we'll talk also a little bit about gallium oxide for MOS capacitors with two different types of oxide layers. Of course, gallium oxide is an oxide as well for the gate dielectrics, silicon dioxide and aluminum oxide. And then I'll summarize the talk. So why these wide bandgap semiconductors, or what are they? Well, we know they are materials that have a large energy gap, and in general, it's an energy gap larger than 3 electron volts. And here I listed some of them: silicon carbide, gallium nitride, gallium oxide. Of course, there's also aluminum nitride and diamond, but I just focused mainly on the ones that we have looked at, although I'm not going to talk about gallium nitride today. But basically, they have silicon, of course, is a very good material for devices and is used a lot in all the electronic devices right now. But it's not a good material for some applications, especially like at high temperature, high power applications. So for those, that is necessary to have other materials like this wide gap materials, and especially we want materials that have high critical fields. So they have a basically high critical field like here for blockage and high thermal conductivity, because all these devices will generate heat. So we want high thermal conductivity to dissipate the heat. And also we want them to have a high, well, I always forget what this is, the Baliga figure of merit, which is there's several figure of merits that have been defined for these wide gap materials. This definition in particular is typically used for electronic devices. So as you can see, and this is all compared to silicon. So here are the properties of silicon, and this is all normalized to silicon. So that's why silicon has one BFMOM figure of merit, whereas all these other wide gap semiconductors have much higher figure of merit. So they would be in general better, right, for these applications. So this graph shows excuse me, the breakdown field as a function of the energy gap. And you can see silicon is right here. So that's why silicon is not really very good for high voltage applications or high power applications. So here's 4H silicon carbide and gallium nitride, and gallium oxide is here as well. So, and this is the beta phase of gallium oxide, which is monoclinic, and aluminum nitride is over here. So these all have very good properties compared to silicon. However, there's some issues, and in particular for silicon carbide, one advantage of silicon carbide is that it has a native oxide, which is silicon dioxide. So it's the same type of oxide as for silicon, exactly the same material, silicon dioxide. So it can be easily integrated with silicon technology. So that's a big advantage for silicon carbide. However, there's some problems with it, and that's why it's not used all the time. I mean, there are already devices that are commercially available that are based on silicon carbide, but it's still not fully applicable at the moment. And that's because there's several issues with it. And some is that there are some electrically active defects that basically reduce the carrier mobility or decrease also the reliability and the stability of the devices over time. So there's several annealing treatments that have improved the properties of the silicon carbide with the silicon dioxide. So the channel mobility with no treatment, just by the growth of the silicon dioxide, is about 10 centimeters square per volt second. However, if there's annealing under different conditions, like with nitric oxide, it increases to somewhere between 35 to 45, or with phosphorus, it increases even more. And you can see here, this is the graph for the phosphorus, and depending on what is the side or the face of the silicon carbide, it can improve. So this is for the what is called the silicon phase, and this is for the A phase. So there's sorry. Yeah, the A phase is the blue one. So you can see that there's a big improvement compared to the samples with no annealing treatment. And same thing for boron, it also increases when the boron annealing to about 180 to or 100 centimeters square per volt second. So what we're interested in is finding out how these treatments affect the interface between the two materials, the silicon carbide and the silicon dioxide. But first, I'll mention a little bit about silicon carbide. So there are over 250 different polymorphs of silicon carbide. And here, this is the structure of silicon, which is cubic structure. This is cubic, it's a silicon carbide that is called 3C. So it's very similar to silicon, but half of the atoms are replaced by carbon. And it still forms what is called a zinc blende structure, basically. But then there's also some hexagonal structures that are called the 4H or 6H because of the number of layers along the C-axis. So these are hexagonal, and this is actually the one that we have been investigating because it has high energy gap, the 4H. So another problem with silicon carbide is that the wafers are still very expensive. I'm not sure if this is up to date, but they are still several $1,000s for a 3-inch wafer compared to maybe like $60 or so for silicon. So they're a lot more expensive. And like I said, the interface traps limit the mobility in the inversion layer. So that gives rise to limits in the threshold voltage. As we can see here, this is the threshold voltage as a function of the bias stress that was applied to the material at different temperatures. So with temperature and increase in bias, the threshold voltage increases. And this is for forward bias, and this is for reverse bias. So there are some issues, and we want to know like how this affect the properties, right? So for example, the nitric oxide post-oxidation annealing, like I said earlier, increases the charge carrier mobility. This would be without any post-oxidation annealing. Treatment is very, very low, whereas after the annealing treatment, the mobility increases quite a bit. And I'll show you, of course, for the phosphorus and boron annealing, it increases even more. So what we want to know is what's the nitrogen doing at the silicon carbide silicon dioxide interface to improve the charge carrier mobility. For gallium oxide, this is a relatively new material as far as making devices or high wide bandgap semiconductor devices with it, but there's already some studies on some investigations on using gallium oxide for Schottky barrier diodes or for photoconductivity. But there's also still problems, like, for example, the temperature increases in the device, and that's definitely an issue. As the power increases, the temperature of the device increases. So that's something that has to be dealt with. But there are more and more studies of gallium oxide, using gallium oxide as a wide bandgap semiconductor for devices. So we have investigated 3 different sets of silicon carbide with silicon dioxide materials, and we've got our samples from Auburn University. We have a good collaboration with them. So one set is basically silicon carbide, silicon dioxide MOSFETs that were post-oxidation annealed under nitric oxide for different times, from 0 to 240 minutes, where they observed that there was an increase in the charge carrier mobility with the annealing time. So we wanted to see how that affected the interface. We also looked at different samples that were grown on different phases, like basically whether it's a silicon phase or on axis or with a 4-degree miscut, or what is called the A phase. And I'll show you in a little bit what the A phase basically has 50% carbon, 50% silicon atoms, whereas on the 0001 phase is either all silicon or all carbon, depending on what phase you're looking at. So we were looking at the all silicon atom phase. And then we also look at some samples that were annealed under phosphor oxychloride or boron oxide on their argon atmosphere to see what was the effect on that, because that increased the charge carrier mobility. So what we do at Maryland is we make TEM samples, and we use the focus ion beam /SEM to extract the TEM lamella, and then we do high resolution TEM, and of course scanning TEM with electron energy loss, looking at the silicon L2-3, the carbon K, oxygen K, and for the samples that had the phosphorus or boron annealing, we also look at the phosphorus L2-3, and for the boron samples, the boron K edges. And we use the spectral unmixing using a HyperSpy, which is a machine learning algorithm that is basically designed to analyze EDS or EELS data in the TEM. So this is just an image of how do we make the TEM samples. And this was for a silicon carbide MOSFET where the gate contact had been removed. So in this region that we wanted to see under the gate contact, so we deposit some platinum protective layer, and then with the ion beam, mill some trenches, and eventually just remove a very thin lamella or sample with using this micromanipulator. Then this is attached to a copper grid, and here's a picture of a copper grid that has posts, and right on one of the posts, which is shown here, we attach the sample, the lamella. And this is sent further using the focus ion beam until it's electron transparent, and then we put it in the electron microscope, in the transmission electron microscope, to analyze this area. So this makes very thin samples that are basically the whole thing is pretty thin, and that way we can, it's very good for electron energy loss spectrum. Yeah, yes, of course, there's always that possibility. In general, what we do, especially at this stage, we go to lower and lower voltages and currents to minimize the damage. But there's always maybe a very thin layer of damage at the surface. The reason we deposit this platinum layer here is for protection, because the ions are coming basically in the normal direction to the sample here. So we do see that in that platinum layers, you can see there's still some platinum here. We do see, we use gallium ions, I should have mentioned that, and we do see some gallium implantation. So, but we make it thick enough so that there's no gallium implantation, at least not enough, not visible in the sample. But yeah, that's always a concern. So here, this is a HADF of high angle annular dark field image, where we select an area that is called, with Gatan software, they call it a spectrum image. And then we raster the beam. So we're scanning the beam in this area and collected an EELS spectrum at every point. So every pixel actually has an EELS spectrum. And at the same time, we're collecting the high angle annular dark field image from this area. So this basically is the same as this area. So here, it says here, this is the silicon carbide and this is the silicon dioxide layer. So of course, never mind. So like I say, in each pixel, there's a spectrum like this. So there's, we can see what is called the zero loss peak, a plasma peak. There's a silicon L23, the carbon and oxygen edges are here. And then we actually fit the background and remove the background so that we can get a signal, which is what is analyzed. So here again is the signal from this pixel after background subtraction, and we can see what's the yield spectrum from this area. So this is silicon carbide, this silicon dioxide. So this would be the silicon edge. This is the carbon edge, and the oxygen is at 532. So there shouldn't be any oxygen here. So if we can actually sum several pixels, and this intensity increases just to improve the signal to noise ratio. Because this is all silicon carbide, we get basically the same kind of spectrum, just so this is just the sum of all the spectra along this red rectangle. So then we can, went the wrong way. We can move to the interface and do the same thing. And you can see that the actual shape of the signal is a little bit different compared to the silicon carbide. So right at the interface, there's some difference. And then if we do the same thing in the silicon dioxide, and now it's in yellow, you can see that it's all even, there's more difference, right? And now we can see the oxygen over here. So we can label this. That's the silicon L23 edge, the carbon K, and the oxygen K edges. And we can use this to analyze the data. Oh, no, this is what is called the fine structure, electron energy loss fine structure. So all this is the signal of silicon. Right. So basically what EELS is, that's a good question actually, because EELS basically, there are no, these peaks, don't call them peaks. So they are not like Lorentzian or Gaussian in shape. And what happens is that this corresponds to transitions from occupied states in the valence band to unoccupied states in the conduction band. So that's why there's a sharp, in general, a sharp increase is where would be like the minimum transition. So corresponding to the energy gap, basically. And then all this is transitions to higher energy levels within the conduction band. So this has a lot of information. It's just not very easy to interpret, but it's a lot of information on the conduction band. Yes? Yes, it starts at 100 eV. That's a good question because that's the energy for transition from the 1s to the from transitions to the L 2p level to the 1s level in silicon. That is about 100 eV, and it's actually slightly different. Maybe if I go back. I don't know if we can see. That's also what we measure. This is actually 100, pretty much 100 in the silicon carbide, but is, oops, sorry, I went the other way. It's hard to see. There's a slight shift to higher energies for silicon dioxide. It's at the 104, okay? And that is actually because those transitions change depending on the material, and because the energy gap is higher for silicon dioxide, it also increases. So, and that's also what we use to measure this. So here, there's this spectra basically focusing on the silicon L2-3 edge, and this is a spectra moving from pure silicon carbide to pure silicon dioxide. So, and shows that shift that I was mentioning. So it's around 100 for silicon carbide, and around 104 for silicon dioxide. Okay, so and this happens over some width of the from the pure silicon carbide around the interface, basically. So that's actually what we use to measure. We measure the inflection point. So this is how the edge, the silicon L2-3 edge shifts from pure silicon carbide, and this is pure silicon dioxide, and this is, it basically shifts over some range of some width of the thickness. So it's 7.3 nanometers for the sample that was not annealed, and the sample that was annealed for 240 minutes, it basically becomes thinner, right? So it more quickly changes from pure silicon carbide to pure silicon dioxide. So that's the result of annealing under nitric oxide. And it actually, so this shows how the transition layer width decreases with annealing time. So for the non-annealed sample, it's about 7.5. And then for the annealed sample of 240 nanometers is 2.5 nanometers. So this also correlates with the charge carrier mobility that was measured at Auburn University. So where they saw that now annealing time is in this direction. So the samples that were annealed longest had the highest peak mobility, and those had the narrowest transition layer width, right? So there was a very nice correlation between the annealing time with charge carrier mobility and the width of the transition layer, right? So this annealing decreases the transition layer width and increases the electrical, the charge carrier mobility, right? So it also reduces the interface traps. So now moving on to the samples that had different substrate orientations. Here's a schematic of the just the structure of the 4H silicon carbide is hexagonal. And so this would be the 0001 phase, and that would be all silicon, and this would be all carbon atoms at the bottom phase. And this is the A phase, so it's just a, in particular the 1,1 bar 2 phase. And this has 50% carbon and 50% silicon. So we wanted to see what was the difference by growing, growing the oxide on the A phase compared to the silicon phase and the 001 phase. So some samples were only oxidized and some samples were annealed for 2 hours on their nitric oxide. So same thing as what I showed you before, but now comparing samples that were on the silicon phase on axis and some that were miscut with a 4-degree miscut and the A axis, the A phase. So we did some high resolution TEM image, and these are without the NO anneal for the silicon phase with 4-degree miscut, silicon phase with 0-degree miscut, and the A phase. So it's a little bit hard to see, but there's actually some atomic steps here on the sample that is miscut because the surface was 4 degrees of the 0001. And these are the ones after annealing, basically the corresponding ones, but after annealing. So by high resolution TEM, they all look very good. We cannot really see a difference because we need basically more detailed analysis, and that would be that's what we did with this EELS data. So this is just another way of plotting the data that I showed you before, but the samples that had 4-degree miscut on the silicon phase, and with annealing time, the width of the transition layer decreased. And these are the new sets that was a sample with 4-degree miscut, and then 0-degree miscut, and this is the A phase. This was just comparing pure silicon, right? The width of the transition layer in pure silicon is really, really small. It's less than 1 nanometer. So it's interesting that in this case now, the red bars here are only oxidized. So only the oxide was grown. And the blue bars correspond to the samples that had the post-deposition annealing on their nitric oxide. So in this case, we actually see an increase, basically with the arrow bars, is basically no difference here. But for the A phase, there's an increase in the width of the transition layer after the annealing. So we want to know what's going on there. So, oops, did I say, oh no, it's okay. So we use HyperSpy, like again, I said, is a machine learning algorithm that is basically designed for analysis of EDS and EELS data. And we use what is called the principal component analysis of the non-negative matrix factorization to basically analyze this data. So this is just examples of spectra that you can obtain. And what this machine learning algorithm does is looks at all the points that have similar spectrum to this or this or this, and basically combines them and tells us what are the main components that will describe the whole data set. Okay, and you can select how many components are necessary. So, so this is easy, and it's easily accessible. It's free, actually, so it's nice software to use. So with this analysis, we can see that in this sample, at the interface, when there's only basically annealing, non-annealing of the sample, we can see that there's really 3 components. All this area in blue has this spectrum for the silicon L23 signal. The green is slightly different. So all these regions have the same spectrum. And in the silicon dioxide, we see this other spectrum. So you can define basically that there's only 3 components in this case. And the question is this one at the interface corresponds to just a linear combination of the 2 from silicon carbide and silicon dioxide, or is it something else? Okay. So, so this again is for the purely oxidized sample. We see 3 components in general. So we have the what we call just a background signal. There's always like a background signal. This signal corresponds to the silicon carbide, and this is for the silicon dioxide. So, and there's basically only 3 components. There's always more components in this plot, but they don't really add anything. Is usually just noise. But we can see that after annealing, we actually need to add we get another component, and that's this one at the interface. So there's always a background component, and then we have the silicon carbide and the signal for the silicon dioxide. But now we have this signal for the interface, and when it's mapped out, it really is at the interface, right? So that's this. This analysis allows you to see where the different components are on the sample. So this clearly shows that it's at the interface. So, so this, basically, I just said that. So this was the same basically for all samples, this in particular for the A phase, but this is analysis of the silicon L23, and it's just basically shows all of the samples show the same thing, that there was an interfacial component. We also, so this again is the silicon L23, and we compared this to data from this paper by Skiff, where they do basically look at nitrogen in silicon nitride, the nitrogen signal, and we can see this is the theoretical, and this is their experiment, and our data from the interface. This is the interface. These are the interface from the silicon phase on axis. This is silicon phase on the 4-degree miscut. This is the A phase, which looks like it's shifted towards lower voltage at by 1.5 eV. And we measured actually silicon nitride. It looks a little bit different, but we actually see that this spectrum looks a lot like the theoretical spectrum. And we think that is an indication that we have nitrogen at the interface. And this actually agrees with SIMS that was obtained from this same sample. They did the SIMS profile, and they actually shows that there's some nitrogen at the interface. So we actually looked for nitrogen in the EELS spectra. The nitrogen KH is at 400 eV, but we couldn't see it. So it probably is just too low for EELS to see, too low concentration. And I should know what the concentration was by SIMS, but I forget right now, but it was low, but enough for SIMS to see it. But we think that we have an indication of the nitrogen at the interface, and that's given rise to this interfacial peak. So we also see, from looking at the carbon KH, we also see a similar effect, that there's a component at the interface, right? So carbon, of course, there's only carbon in the silicon carbide. So that's the signal from silicon carbide. And this is at the interface, we see this component. So there's an indication that we think that there's still carbon bonded to nitrogen also at the interface. So this is from a paper from Hu et al., who looked at nitrogen incorporation in a nickel carbide sample. And as they increased the nitrogen, could see a change in the carbon KH in the EELS spectrum, going from a more SP3 to SP2 type of bonding. Whereas in the EELS spectrum, this peak corresponds to a transition from the 1s level to the pi star unoccupied orbital. And this corresponds to the transition from the 1s to the sigma star orbital. So you can see it becomes more sp2 kind of bonding with increasing nitrogen. So we think that that's also what's happening in these materials, in the silicon carbide. For the oxygen KH, we only saw this an effect of at the interface for the sample that was deposited on the A phase, and with the sample that was annealed on the nitric oxide. So we have this interface oxide. So that also, when we map it out, is right at the interface, and this is just what the silicon dioxide, the oxide, would be. So, so only for some reason, only the A phase has showed that behavior. So let me just summarize this part of the talk. So we confirmed that there was some effect of the nitrogen in the we call it silicon nitride-like bonding from both the silicon L23 and the carbon KH. The carbon bonds have sp2 character where in the NO annealed devices. And the oxygen interfacial signal was only for the A phase and annealed samples. And we also see, of course, that we have in decrease in the width of the transition layer with annealing time, and that correlated with the improved charge carrier mobilities. Sure. That's a good question. Yeah. I don't know for sure. Because normally you need, you need that oxide, gate oxide, right, layer for the MOSFET. But that's a good question. I don't know. That would be interesting to do actually, but I don't think that it's been done. But I don't know. So now let me just mention something about the samples that were annealed under phosphorus or boron. So it was a phosphorus oxychloride annealed at 1,000 degrees after, of course, the thermal oxide growth. So this was about 60 nanometers growth. And then also the samples were annealed under borium oxide with an argon gas atmosphere. And again, we did a TEM. So I already mentioned this, that the charge carrier mobility increased for the samples. This is for the boron samples and the phosphorus samples, and there was an increase, even more higher increase for the samples that were grown on their A side, A phase of the silicon carbide. So this is a high resolution TEM image of the sample with the phosphorus. So the phosphorus anneal creates some phosphorus silicate glass layer, but we cannot really see much detail here, right? Except it looks pretty nice. Here, this is the high angle annular dark field, which basically is a form of imaging that is sensitive to the atomic mass. So high atomic mass will look brighter because they basically scatter electrons more strongly. But it still doesn't really tell us what's going on, except that we see, here's the interface, this line is the interface, and we see some region here that is kind of darker. And then here we see these white blotches, right? So by doing EELS, we can analyze what these are. And basically, we can see that in this case now there's several components when we do the principal component analysis. There's several components. Of course, there's always a background. There's a silicon carbide signal. And then for the phosphorus, it looks really, really weak. Here is where the phosphorus L23 edge is. If we map this out, then we can see like this region, these clusters of about 3 nanometers in diameter. And some weaker signal all through the silicon dioxide. But something that is interesting is that there's 2 different signals for the oxygen. There's that we just call them oxide 1 and oxide 2, and they're more or less in different parts. So they are like sub-oxides, maybe not necessarily SiO2, it could be SiO2 minus X or something like that, that are in different parts of the silicon dioxide layer. One of these is more like silicon SiO2, and this is like a sub-oxide layer, right? But we can see this clusters of about 3.6 nanometers in diameter. For the boron anneal samples, this is again the high angle annular dark field image. I don't know how hard it is to see. There's a very thin layer that is a little bit darker right here. It's about 1.5 nanometers in width. And by EELS, we can find out what that is. Again, so that's, in this case, we have like, again, the background signal, the silicon carbide signal, and the boron. Now we can see clearly a boron K edge. And when we map it out, we can see that there's pileup of boron right at the interface. So it's similar to the nitrogen case, the nitric oxide annealing. But now boron is going to the interface, but there's still some boron in the silicon dioxide layer. But if we get the profile of this boron, here's where the interface is. We can see basically high concentration of boron here, a little bit of a depletion as we go away from the interface into the silicon dioxide, and it kind of changes the profile, but it's there's still some boron in this region. But it's also interesting that there's some boron going into the silicon carbide, and we believe that it's probably acting as a dopant, right? And boron acts as a dopant in silicon carbide. So this is also another sample that was also with aniline with boron oxide at 950 degrees C, and we can clearly see again that there is higher boron concentration at the interface. Oh, oops. Sorry, I think I forgot to. So this is just basically, again, the plot of the profile, and we can see that there's higher boron near right at the interface, and some boron going into the substrate. I'm sorry? Okay. So just to summarize this part, we have that both phosphorus and boron incorporate in the gate in a different way than the nitric oxide. The phosphorus distributes forming clusters of about 3 nanometers in diameter, and the boron segregates preferentially to the interface, and some diffuses into the silicon carbide as well. But the distribution is not perfectly uniform. Now I want to switch. We still have time, right? Yeah. Okay. To gallium oxide, and we don't have as much research on gallium oxide, but it's been interesting. So we have the samples that have a silicon oxide, basically gate capacitor, and others with aluminum oxide, and we have some correlation with electrical measurements. So we also investigated the interface between these two. And I also want to show you some interesting results we found of crystallization of the aluminum oxide under the electron beam. So these samples were like for the silicon dioxide and the aluminum oxide, we had 2 sets of samples. One was the SiO2 was grown by low pressure CVD at 650 degrees C for 45 minutes. And then it had a post-deposition annealing at 850 degrees C for 2 hours under nitrogen gas. And the other sample was a low temperature oxide growth at 400 degrees C with a post-deposition annealing at 1,000 degrees C for 60 seconds. For the aluminum oxide, one sample was deposited at 250 degrees and with no post-deposition annealing afterwards. And the other one was basically the same growth, but it was annealed at 500 degrees C for 2 minutes under forming gas. So these are the structures. They had aluminum contacts for the electrical properties measurements. So for the silicon dioxide, gallium oxide, silicon dioxide interfaces, here are the high resolution TEM images. These are 2 different samples. Unfortunately, here's the gallium. Unfortunately, they are kind of flipped, but the gallium oxide is crystalline. The silicon dioxide is amorphous, and we see some roughness of the interface, localized roughness. This was the sample grown by low pressure CVD. This other sample that was grown at low temperature but annealed at 1,000 degrees C had more roughness. Some areas look kind of flat, but others had some roughness, localized roughness. So by doing the same thing as we did for the silicon carbide, we had the gallium oxide and silicon dioxide layers here. This is the silicon L2-3 edge, so here, and the gallium oxide. So here are the 2 spectra, the spectra, the silicon L2-3 and the gallium M. So you can see basically what we expect, right? Gallium oxide here. And if we plot the profile, we can see a fairly sharp interface of about 1.8 nanometers width, and we define the interface from the shoulders here. the width of this. However, now for the aluminum oxide, it was interesting, and we can see that the sample, this is all aluminum oxide that is amorphous, and we see a very thin layer of about 1.5 nanometers that is crystalline, is the epitaxial aluminum oxide. And what we observed, and I'll show you a video later, is that after some time, this will crystallize, and we'll see large areas that are crystalline here. And this was also for the sample that these were two different samples, and we always observed the same thing. So I'll show you a video later of the crystallization. But we also did the same analysis, and this is a sample that had no post-deposition annealing, so just basically the growth of the aluminum oxide. And we can see basically the aluminum where we expected, gallium, nothing at the interface. But we do see a relatively sharp 3.2 nanometer interface. Maybe a little bit of gallium diffusing into the aluminum oxide. With the post-deposition annealing, we can see that actually the interface becomes wider. So it's now 5.6 nanometers. So this is kind of opposite to what we found in the silicon carbide with the silicon dioxide, where the width of the transition layer decreased with annealing. In this case, it's actually increasing with annealing. And we can see that the gallium, especially the gallium, is going deeper into the aluminum oxide upon annealing. So this is also showing pretty much the same thing, where looking not only at the gallium and aluminum edges, but also the oxygen the oxygen signal in gallium oxide is different than the oxygen signal in aluminum oxide. So plotting also all these signals, basically, we can still see pretty much the same thing with no annealing, post-deposition annealing. The width of this transition layer is, oops, I'm afraid this time. So I think I have one here. Oops. So with the post-deposition annealing, this becomes wider, about 4.7 nanometers. And we believe that maybe there's some oxygen vacancies and there's obviously some diffusion of gallium into the aluminum oxide and maybe some aluminum into the gallium oxide. Oh, thank you. I prefer green. Thank you. So this is basically the correlation to the electrical properties. This is the density of interface traps, and it decreases with increasing EC minus ET. So we can see that it's higher for the samples that had the silicon dioxide, and it's smaller for the samples that had the ALD, atomic layer deposition of aluminum oxide. So there's some correlation. It's not a perfect correlation, but with the traps, the interface traps, and the width of the transition layer. So this is higher for the sample with the silicon dioxide, which has a slightly higher thickness of the transition layer. Okay. So now I want to show you this video of the crystallization. Oops, it doesn't work. I have to do it here. Oh, I think it's running now. Okay. So this is a relatively low magnification, and you can see, hopefully you can see this profile. This is crystalline, and this is amorphous. So we had already been looking at this area when we suddenly realized that this was happening and is increasing in this direction. And in a second, we are going to move to an area where that has not been exposed to the electron beam. And we just kind of moved along in this direction. I'm sorry, I should have mentioned, this is the silicon carbide, I'm sorry, gallium oxide. This is aluminum oxide. Okay, and so we'll move very soon. So this is now at higher magnification. You can see now the scale change. So this is high resolution. And of course, the beam size is larger than the field of view. So we can see, hopefully you can see the profile moving here. And it will move again a little more. So, come on. So we have to move to an area that had not been the beam. So here's an area, and you can see, hopefully you can see it's amorphous. Later, we actually inserted a square to get the fast Fourier transform. You can see the profile, the crystallization front moving in this direction, right? And hopefully you can see that there's lattice fringes, lattice planes here. And so now we introduce this square to get the fast Fourier transform. And again, we're moving to a fresh area that had not been exposed to the beam. So you can see here, this fast Fourier transform indicates that it's amorphous, right? There's no spots. And then here's the crystallization front. And now we can start to see some spots forming here because this is becoming crystalline. And basically the whole film becomes crystalline. It's a single crystal. It has the same orientation everywhere. So that's a good question. The timing depends on how much we converge the beam or how much it's spread. And it's roughly 1 minute, but that depends on how converged the beam is. Yeah, I have that. Yes, I'll show you in a second. I don't remember off the top of my head. So here again, this is another area, and we just kept on following this. And as you can see, it's hard to tell just from this fast Fourier transform, but it's the same orientation everywhere. So there's crystallization coming from the area that was already crystallized, but also from this interface. So this is just like a snapshot of those frames, some frames. So this is where it's still, where we just start looking at it. It's amorphous, so the fast Fourier transform shows just broad rings. And so this is like, as fast as we can focus on the area, so maybe less than 3 seconds when we move to this area. And we see this 1.5 nanometer crystalline layer here. After about 10 seconds, we can see that this is already becoming crystalline. So the spots are still kind of broad and weak, but they become stronger. And after like a minute, it becomes all crystalline. And here's just this a line to show where the crystallization front is at this time. So this is the fast Fourier transform from the gallium oxide, the fast Fourier transform from this area from the aluminum oxide. And it's always the same orientation for aluminum oxide. So we analyzed these areas. So this is just comparing two fast Fourier transform from two different areas, and it's the same diffraction pattern. So it's always it becomes a single crystal film. Same orientation. It's actually with the gamma aluminum oxide, which is a cubic phase. Whereas the gallium oxide is a monoclinic phase. So a beta is beta aluminum oxide. So here, just if we compare the oxygen layer of the gallium oxide, beta gallium oxide with the bar 201 normal to the 111 aluminum oxide with the gamma phase, they're very, very similar. Right, and it would have a lattice mismatch that is pretty small lattice mismatch, and we think that's why we get this orientation and this structure, because it minimizes the lattice mismatch along these two different directions, right? So the 102 of gallium oxide is parallel to the 11 bar 2 of aluminum oxide, and 010 direction of gallium oxide is parallel to bar 110 of aluminum oxide. So this is basically the same thing, just put in the layer of gallium oxide with the bar 201 surface and the aluminum oxide with the 111 surface, and it's pretty closed structure. So we basically looked at samples, basically repeated this experiment on several samples, changing the voltage from 100 kV to 200 kV, changing the dose of the electron beam, spreading it or converging it or spreading the beam, and actually measure the beam intensity and dose. And here we basically see that the crystallization front of the speed, it depends on how converged the beam is, basically the current density. So this roughly is 2.3 nanometers per second. This was at 200 kV. So we actually changed the beam diameter that changes the current density, and these are for 200 kV electrons. And we have the crystallization front rate changes. Of course, if we spread the beam, we lower the current density. The crystallization front moves more slowly, and so it takes longer. So with a converged beam, it would take 18 seconds to crystallize, but with a spread beam would take 60 seconds. But the total dose was basically the same. Regardless, so just because it takes longer, if we have a weaker or lower current density, but the total dose is the same. And similarly, for 100 kV, we basically did the same thing, have a converged beam or a spread beam, which changed the current density, and we'd also would change the crystallization front, the speed of the this is the crystallization front rate and the time to crystallize, but we also get essentially the same dose overall, but you can see that this is lower than this. So it crystallizes faster at lower voltage, which is an indication of something that's called radiolysis mechanism, which is basically that the electron beam is giving rise to movement of the atoms in the material to make them crystalline. I should mention also that we also looked at when I started talking about the gallium oxide, aluminum oxide samples, I said that one of the samples was annealed at 400 degrees C. That's below the crystallization of temperature of aluminum oxide, which is around 700 degrees C. So that sample also was amorphous when we started looking at it, and it also crystallized the same way. So we looked at samples that were not annealed, samples that were annealed. So this is really an effect of the electron beam, not temperature. Oh, sorry. This only happens. You can see in this here. This is the whole film, right? We didn't have like really thick films to like, you mean like put the beam here and see if the same thing happened. That would be good, but our beam in TEM mode, we probably, because this is 60 nanometers, the thickness, so maybe, I don't know what would be the smallest spot size in TEM mode. In STEM mode, we can make it much smaller, but this was all in TEM mode. So to answer your question, we didn't do that. Here, this is an aluminum contact on this side. So. Like this one? Mm-hmm. The real answer is I don't know for sure, but it could be just a slight misalignment or something. I don't think this is, even though we got pretty nice diffraction, well, this is a fast Fourier transform, but, oh. Mm, yeah, yeah, I don't, it's possible, I think, but I don't know for sure. I'm almost done. But so we also, just to make sure, we calculated the increase in temperature, because when we're bombarding the sample with electrons, the electrons could increase the temperature of the sample. So we calculated the temperature using a formula from Egerton based on the electron energy loss spectrum. But we also use a finite element analysis model because we know what our sample is. This is a schematic of the structure. This is the copper host, and here's our sample. And the beam was pretty small, localized here. So we know the thermal conductivity of gallium oxide, of aluminum, and copper. So we use all that to calculate, estimate the change in temperature. And we got that it was like the increase in temperature was 0.2 Kelvin at most. So both methods gave us very low increase in temperature. So what we know that the samples, the aluminum oxide crystallizes at 700, and we definitely did not go to 700 degrees C. So, so this, I think I pretty much covered this. This was interesting because this other paper by Hattori et al., they grew aluminum oxide on gallium oxide. This was 010 beta gallium oxide, and they obtained crystalline aluminum oxide, but with a different orientation, the 440. So the orientation was different. The relative orientation between the two materials was different than what we observed. But they still have a low mismatch. So there's different ways, I guess, of aluminum oxide can crystallize on gallium oxide. But this was a different phase, the 010, and ours was the part 201 normal. So I just want to briefly summarize that for the silicon carbide and silicon dioxide, we have confirmation of some evidence of nitrogen at the interface. We see that the NO anneal basically creates some bonding between in silicon and carbide with nitrogen. We see that the carbon bonds have sp2 character primarily, but the oxygen interfacial signal did not alter so much except for the A phase. And the thickness of the transition layer decreased with annealing time under a nitric oxide and had a correlation with an increase in the mobility. For the phosphorus and boron samples, we see that they both incorporate in a different way than the silicon, than the nitric oxide incorporation. Phosphorus distributes into some clusters of particles inside the material, and which could have an impact on the properties. It could maybe use to design different devices. I don't know. The boron preferentially segregates to the interface, and in some of it diffuses into the silicon carbide. And for the gallium oxide, we see that silicon oxide has some roughness of the interface, but the interface is relatively narrow, about 2 nanometers wide. For the aluminum oxide layers, there's more diffusion of gallium into the aluminum oxide, and it gets worse upon annealing. And then we also observe this crystallization of the aluminum oxide under the electron beam, which raises the questions of how this could affect devices. Could this also happen when the device is, it's been used or whatever? So that would have to be determined later. I just want to acknowledge our collaborators, especially Josh Talon and Christopher Kleinschenk, who were the students that worked on these projects and got their PhD thesis at the University of Maryland. And then these other co-workers, some from the University of Maryland, Auburn University, and Rutgers University, and John Cummins at the University of Maryland, who also helped us with the measurement of the dose for the crystallization project. And definitely, I want to acknowledge the support from the Army Research Laboratories and NSF, who had provided a graduate research fellowship for Josh Talon for his PhD, and of course the use of the facilities at the AIM lab at the University of Maryland, and the HyperSpy algorithms, which were very, very useful for us for our analysis. And thank you, and I'll be happy to take questions. How to prepare the fifth sample for TEM? Oh, it's a method that is being basically, I was amazed at first when I heard like making samples with fifth. You basically select the area you want, deposit a protective layer, and then because the advantage of the FIB is it has ion gone and an electron gone, right? So you use the ions to mill the surface. So it's kind of like scooping out material. So you define an area on the surface of the sample. You make a square or rectangle, and then the ion beam is rastered in that area, and that's removing material. So if you remember, I mentioned they have two. Maybe I can go quickly back. Oops. Okay. So here you define your area, then you basically draw a square with the with computer, and it mills out this area, and you keep going closer and closer to the center of the area that you're interested in, and eventually you make something that's called a U-cut by milling at an angle. You basically mill through this area. Once it's thinner, I guess there's one step that is missing between these two. And then you bring a nanomanipulator that you bring it close to the sample, and it touches here. Basically would be right here. It would touch when this is thinner, and you deposit with the gallium ions or the FIB. We use gallium ions. You can actually deposit, introduce a gas. So when I say here is a protected platinum, it's not pure platinum, it's a metal organic film that has platinum, but there's a lot of carbon in it as well. So you deposit more of that here, and then you make the final cut. And then basically to free the sample. So free it from the substrate, basically. But now, because it's attached to this nanomanipulator, you can lift it out. And that's the scariest part, because it can touch something and then it goes flying. So you lose a lot of samples along the way. And then the grid here is sitting like this, and another part of the chamber, and you bring the nanomanipulator and just gently touch the sample, the other end of the sample here, this edge, to one of the posts. This would be rotated with the fingers like this. And then you bring it like just barely touch. And that's another point where it can break if it touches too hard. It just, shatters. And then deposit with the ion beam more platinum, or it could be platinum, carbon, tungsten, there's different materials. And then with the same ion beam, the sample would still be attached to this manipulator. So you cut it free. So you cut that, and then just mill more until it's electron transparent. Does that help? When my student Josh started making samples, the first time it took him 10 hours to make one sample. But like everything, the more you do it, the better you get at it. It still takes time, but it's so important to make good samples that it's a very important step. Thank you. So.